What if a single localized disruption on the small island could trigger a worldwide industrial paralysis? This is the precarious reality of our modern economy. Taiwan produces over 60% of the world's total microchip supply and over 90% of all advanced logic semiconductors. This extreme geographic monopoly creates a silicon shield because global superpowers have a massive shared interest in preventing conflict in the Taiwan Strait. If Taiwan's foundries stop, the entire modern world stops with them. Taiwan occupies a high value, high complexity bottleneck that is incredibly difficult to replace in the short term. This island produces more than 90% of the world's most advanced logic chips. These microscopic silicon chips serve as the critical brains for artificial intelligence systems, cloud data centers, flagship smartphones, and advanced military equipment. This massive technological concentration was enabled by TSMC's pure play foundry model, which manufactures chips for other companies without designing its own. In 1987, Dr. Maurice Chang established TSMC with backing from the Taiwanese government. He pioneered the pure play foundry model. Before TSMC, chip companies designed and built their own silicon. Chang realized that manufacturing was becoming too complex and expensive. By promising that TSMC would only manufacture chips and never design them, he removed any conflict of interest. This built deep long term trust with fabless designers like Apple, NVIDIA, and Qualcomm. The concept of the silicon shield was first popularized by journalist Craig Edison in the late 1990s. The core thesis is that Taiwan's dominance in tech manufacturing deters military aggression. An invasion would trigger a global technology crisis, destroying supply chains for both the United States and China. This shield relies on three pillars: TSMC's advanced technology monopoly, credible security guarantees from the United States, and the prohibitive global cost of a cross-strait conflict. To understand the economic weight of the Silicon Shield, Bloomberg Economics modeled the cost of a cross-strait war. Their findings are staggering. A full-scale conflict would cost the global economy $10.6 trillion dollars in the first year alone. This represents a 9.6% contraction in global GDP, making the shock nearly twice as large as the economic damage from the COVID 19 pandemic or the 2008 financial crisis. The primary mechanism driving a global collapse is the golden screw phenomenon. Advanced logic chips are functionally irreplaceable. If a factory making cars, medical systems, or consumer electronics lacks a single advanced chip, the final product cannot be built. A complete halt in Taiwanese wafer shipments would cause US logic chip prices to spike by over 50%. This would trigger cascading factory shutdowns and massive layoffs across the globe. A gray zone blockade is highly effective because Taiwan is a trade dependent island with deep physical vulnerabilities. Taiwan imports roughly 97% of its primary energy resources and 70% of its food supply. Yet the island generates over 100% of its GDP from international trade. A successful maritime quarantine would stop microchip exports while cutting off the vital energy and food supplies needed for the island to function. A gray zone blockade is highly effective because Taiwan is a trade dependent island with deep physical vulnerabilities. Taiwan imports roughly 97% of its primary energy resources and 70% of its food supply. Yet, the island generates over 100% of its GDP from international trade. A successful maritime quarantine would stop microchip exports while cutting off the vital energy and food supplies needed for the island to function. To counter its diplomatic isolation, Taiwan has pioneered technology diplomacy. Run by the Ministry of Foreign Affairs and the National Science and Technology Council, this strategy builds alliances through high tech cooperation. Their flagship initiative, the widely known Wrong Bang program, seeks to integrate diplomatic allies into ecosystems like semiconductors, green energy, smart agriculture, and artificial intelligence. A prime example is the Taiwan Paraguay Smart Technology Park, which replicates Taiwan's successful science park model abroad. The global race for semiconductor supremacy is accelerating, driven by the artificial intelligence revolution. The market for advanced node logic chips is projected to grow to over $229 billion by 2034. Shipments of chips built at 5 nanometers and below are capturing 60% of the market. TSMC maintains its technological lead, scaling up its 2 nanometer process node with next generation nanosheet transistors and backside power delivery. The absolute choke point of the entire semiconductor supply chain is ASML in the Netherlands. Every advanced chip manufactured below approximately 7 nanometers is made possible by ASML's extreme ultraviolet lithography scanners. ASML is the sole global supplier of these machines. It spent over 10 billion euros in cumulative R&D over 2 decades to develop EUV technology. The barriers to duplicating these sub-sized machines are physical and institutional, not merely financial. Even within ASML's monopoly, there is a deeper choke point. Carl Zeiss SMT. In Germany, Zeiss is the sole provider of the advanced optical systems and mirrors used in EUV scanners. These mirrors must be polished to sub zero point 0.1 nanometer roughness and aligned to picometer precision in high vacuum chamber. ASML cannot manufacture or ship its advanced scanners faster than Zeiss can produce these highly specialized, complex optical mirror sets. While advanced wafer fabrication plants get most of the public headlines, the ultimate bottleneck in the artificial intelligence economy is advanced back-end packaging, specifically TSMC's proprietary chip on wafer on substrate or CoWoS technology. CoWoS integrates logic dies and high bandwidth memory side by side on an ultra thin silicon interposer. This interposer acts as a dense physical communication bridge. Without this highly advanced back-end packaging, even successfully fabricated silicon dies are completely useless and cannot ship as functional AI accelerators. The extreme shortage of advanced packaging has created a massive allocation struggle among global tech giants in 2026. NVIDIA has aggressively locked up 80% of TSMC's advanced CoWoS capacity, creating a powerful supply chain moat for its Blackwell and upcoming Rubin GPU architectures. Because of this extreme concentration, packaging lead times for high end AI accelerators have stretched up to 78 weeks, capping the immediate revenue potential for other hardware competitors. To bypass high-end GPU shortages, cloud giants are building custom chips like Google's TPU, Amazon's Trainium, and Microsoft's Mia. Broadcom and Marvell dominate this custom co-design market, controlling 95% of the business. However, this custom silicon push does not escape Taiwan's monopoly. Every single one of these custom designs is still fabricated on TSMC's advanced nodes and packaged on TSMC's oversubscribed CoWoS lines, ensuring total global dependence for the tech sector. Because of TSMC's oversubscribed CoWoS lines, Google was forced to cut its 2026 TPU target by 25%, reducing production from 4 million to 3 million units. To handle this massive bottleneck, advanced packaging orders are spilling over to outsourced assembly and test partners. In response to this crunch, ASE's subsidiary SPIL acquired Taiwan Mass Corporation's Zonan plant 6 for 2.8 billion new Taiwan dollars to expand capacity. The US push to onshore chip manufacturing face a glaring geographic vulnerability that many policymakers ignore. Under intense pressure, TSMC is building state of the art fabs in Arizona. However, no high volume commercial CoWS advanced packaging facilities exist on American soil. This means that every advanced chip fabricated in the Arizona desert must still be shipped back to Taiwan for advanced packaging. A cross strait conflict would still easily cripple this domestic supply chain. The United States is executing a massive onshore experiment under the CHIPS and Science Act of 2022. This landmark legislation committed $39 billion in direct manufacturing subsidies and $75 billion in loans. The goal is to bring 20% of the world's leading edge logic production to American soil by 2030. As part of this push, TSMC is investing $65 billion to construct three highly advanced fabs in Phoenix and Arizona. Operating in the United States has been a complex regulatory challenge for TSMC's management teams. Unlike Taiwan, highly centralized science parks, the Arizona project had to navigate sequential county, state, and federal permitting processes. TSMC Arizona spent $35 million drafting 18,000 rules just to comply with local building codes. This fragmented regulatory environment delayed volume production at Arizona's first fab by over a year, highlighting the friction of Western onshoring. TSMC's strict militaristic corporate culture clashed directly with American labor expectations in Phoenix. Taiwanese managers struggled with local construction unions over demanding schedules, training, and site safety. Tensions spiked following the tragic death of a worker in May 2024. Furthermore, over 30 American employees filed a major class action lawsuit in US federal court alleging systematic discrimination, linguistic exclusion, and verbal abuse by Taiwanese supervisors, revealing deep cultural rifts that slowed the project's development. While Arizona struggled, TSMC's Japan unit JASM executed a textbook expansion in Kumamoto, supported by over $8 billion in rapid direct subsidies from Japan's Ministry of Economy, Trade and Industry. JASM built its first fab in exactly 2 years. By forming a highly integrated joint venture with local giants like Sony, Denso, and Toyota, TSMC secured immediate local customers and navigated municipal permitting with unparalleled administrative cohesion and speed. Despite construction delays, a startling financial paradox emerged in early 2026. TSMC's Massey, Arizona fab posted a staggering $2.8 billion net profit in the first quarter of 2026. This single quarter profit surpassed its entire full year 2025 net income. Arizona succeeded because it targeted high-end 4 nanometer chips. US tech giants Apple and NVIDIA were so desperate for secure domestic AI silicon that they willingly paid a premium for Arizona made processors. In contrast, Japan's pristine Kumamoto fab suffered severe financial losses, losing 301 million US dollars in 2025. Kumamoto initially focused on mature legacy nodes for the automotive sector. However, while JASM was building, Chinese fabs flooded the global market with cheap legacy chips, capturing a projected 39% of the global legacy market share. This massive oversupply crashed legacy prices globally, leaving Japan's textbook fab struggling with highly unprofitable operating margins. To escape the Chinese oversupply of legacy chips, TSMC was forced to completely re engineer its Japanese manufacturing roadmap. JASM's second fab, which is currently under construction, has been pivoted away from mature nodes and redesigned to manufacture advanced 3 nanometer chips. This financial reality delivers a vital lesson for global industrial policy. You can subsidize the construction of factories, but you cannot dictate market demand or protect against global pricing crashes. The next major technological leap is high NA EUV lithography, which has split the strategies of chip giants. Intel has adopted ASML's first high NA machines to scale up its 18A process node. In contrast, TSMC has delayed adoption of these expensive systems until late 2027 or 2028 due to extreme cost concerns, preferring to optimize its existing EUV tools. This technological divide will determine who leads the sub 2 nanometer era as the industry advances. Many Western leaders believe that building fabs in Arizona or Europe will eliminate our resilience on Taiwan. However, this is a dangerous misunderstanding. TSMC is keeping its most advanced cutting-edge R&D and pilot lines, such as its upcoming 2 nanometer and A16 process nodes, firmly rooted on the island. The facilities built in the United States and Europe represents only a fraction of TSMC's total output, meaning the geographic monopoly remains intact. Taiwan's geostrategic leverage is highly sensitive to offshoring. Critics within Taiwan warn that moving advanced manufacturing abroad could hollow out the Silicon Shield. If the United States and its partners can secure advanced microchips from domestic facilities, their political and military incentive to defend Taiwan from a Chinese assault decreases. The structural shift could erode the technological deterrence that has kept the region stable, transforming the shield into a snare. The erosion of the Silicon Shield has been accelerated by a shift in US foreign policy. Under transactional leadership, traditional alliances and security commitments are treated as commercial transactions. The narrative that Taiwan stole America's semiconductor business has been used to demand that Tapia pay for its own defense. Their commercial conditionality turns Taiwan's security from an institutional guarantee into a negotiable commodity, creating a dangerous window for strategic recalculation. As the global trade war escalates, China is leveraging its own upstream resource monopoly. The nation mines 60% and processes 80% of the world's rare earth elements. Beijing has already placed strict export controls on 12 critical rare earth metals, including samarium, gadolinium, and dysprosium, including samarium, gadolinium, and dysprosium. This rare earth bazooka directly targets Western defense contractors, advanced manufacturing, and green energy industries, demonstrating that the semiconductor supply chain has severe chokeholds in both hemispheres. While hardware remains critical, software breakthroughs are rewriting the rules of the AI race. In January 2025, Chinese firm DeepSeek released a language model of extraordinary efficiency and affordability. This breakthrough demonstrated that advanced algorithms can bypass hardware and EUV restrictions by showing that massive compute clusters are not the only path to AI leadership. DeepSeek triggered a massive sell off in Western hardware giants like NVIDIA, proving software can overcome hardware limits. In analyzing the Silicon Shield, we must avoid a common academic trap. Taiwan is not merely a collection of advanced semiconductor foundries and packaging lines. Technology and GDP data are only specific types of evidence. To truly understand the island, we must look beyond silicon to its rich archaeology, languages, oral histories, culture, and community identity. We must never reduce a living, vibrant nation to microchips or raw supply chain metrics. The silicon shield is not a static protective barrier. It is a fragile dynamic equilibrium that balances high-tech monopolies, security guarantees, and the catastrophic global cost of conflict. As superpowers attempt to onshore advanced manufacturing, they are learning that building ecosystem is a capital intensive process measured in years, not quarters. Ultimately, our global economic stability will depend on maintaining mutual dependency, respecting respecting international sovereignty, and preventing technology from becoming a weapon. Thank you very much. Best of luck.